Log on, tune in, find out. Another good idea from Cambridge.
Bhama Srinivasan from the University of Illinois, Chicago, and she's going to talk about quadratic unipotent blocks of finite general linear, unitary, and symplectic groups.
Thank you. And I thank the organizers for inviting me and also for putting together this wonderful program, which seems to be the cutting edge in Lie theory. So, and please excuse my voice, which is a little strange today because I've got some kind of problem, sore throat. So let's see. So I start with the algebraic group G, which is, can you hear me? Pramod? Then you have the Frobenius, and we take the finite reductive group. So from now on, I will only talk about the finite group because it's too messy to keep writing G upper F. And as usual, I will use the words tori, Levy subgroups, etc. as coming from the algebraic group, F stable, and taking the F fixed points. Now, the first tool that we use is Deligne-Lustig theory, for which you take, now I do need the L in the algebraic group just for the notation. So the Deligne-Lustig operator goes from the Grothendieck group of representations of the finite Levy subgroup L over QL bar to the Grothendieck group of the same thing of G. So it could take a proper character of L to a generalized character. And then we have these very important characters which I think have been mentioned before. Unipotent characters are those which come, especially if you take a maximal torus, they are the constituents of RTG1. One is the trivial character. Now, if it happens that this Levy subgroup is already in an F-stable parabolic, then you get just the usual Harish-Chandra induction. So, after this Deligne-Lustig theory, which is by now quite old, the first paper is in 1976, then Lustig did a classification of the irreducible characters, so it's in good shape. And what I'll use is this fact that the set of irreducible characters is partitioned into Lustig series, which are denoted E, G, S. S is a semisimple element, but the conjugacy class of S can be in G star, the dual group G, which makes things sometimes somewhat complicated. Now we go to modular representations. We have a usual setup. K is sufficiently large field where you can write all the ordinary irreducibles. O is a discrete valuation ring. Then the ordinary characters of G. So the reason why I've written this statement about blocks is that I will be using the word block in two different ways. Over K, if I talk about blocks, it means the ordinary characters are partitioned into sets called blocks. And over O, when I talk about block, it will be an algebra. So that's why I wrote this sentence here. So now let's go back to our finite reductive group, for example, a classical group, and L a prime not dividing Q. So we are dealing with L modular representations of this group G. And the first problem is describe the L blocks of G. So we talked about the special set called unipotent characters. So we talk now about unipotent blocks, which is a block. As I said, block may be a set of ordinary characters. So unipotent block is one which contains unipotent characters. They form a nice important subset of the block, although there may be other characters in the block. So one problem is describe the unipotent blocks. Then let's give an example of GLN, and E is the order of Q mod L, which also occurs in other situations, such as with quantum groups. I think we saw the same Q, E, L. The unipotent characters of G are now easily described for GLN. They are just characters which occur when you take the permutation representation, inducing the trivial character of B. And they are indexed by partitions of n. So let's call this chi lambda the character corresponding to lambda. Then we have an old theorem which is described in combinatorial terms, which I'm giving here because later on it will be generalized with Paul Fong. So chi lambda and chi mu are in the same L block if and only if the two partitions lambda and mu have the same E core. That means combinatorially, as in the classical theory of the symmetry group, you take the Young diagrams, you remove hooks, E hooks, and you get to the same E core. So the interesting point is, as Michel Brouet used to say, Brouwer equal to Lustig. So the Deligne-Lustig theory and Brouwer theory, though they were developed quite independently, they coincide. Now if you have classical groups, George Lustig, as I said, he classified the irreducible characters. So he introduced objects called symbols, which are analogues of partitions. And they are like this, S and T. S is the subset on top, 0, 1, 2. T is the subset at the bottom, 1, 3, and so on. Here, you don't need to draw diagrams. You can describe algebraically the procedure of adding hooks, removing hooks. So adding a 2 hook to the first symbol means you just add 2 to one of the entries, if that is possible. So 0, 1, 4, 1, 3 comes from that. Now we also have the notion of co-hook, which means adding and then moving to the other side. So 0, 1, 2, you added the 2 to the 2, which is 4, and then you moved it to the second row. So this is a combinatorial procedure just analogous to what happens in the symmetry group, which is very classical. And of course this is also generalized by people who work in cyclotomic Hecke algebras. Now again, excuse me, you have unipotent characters parameterized by symbols rather than partitions in these classical groups. I put the C because sometimes you need the connected center. And then Q and L we usually take to be odd throughout. Now, after we proved another paper, in another paper, that unipotent blocks for these groups are classified again by E course of symbols. And exactly similar theorem, if you say psi lambda 1, psi lambda 2 correspond to symbols lambda 1, lambda 2, they are in the same L block if and only if lambda 1, lambda 2 have the same E core. So far the main tool used is delinguistic theory. Then later on, some people, Paul Fong and myself and Michel Brouet, Gunter Mahler, etc., various people, Jean Michel, we developed something called E. Harishchandra theory, which generalizes the usual Harishchandra theory, which is the case E equal to 1. So what we do is so this is also making abstract the idea of core. So the L, we have certain pairs, L and psi, are called E cuspidal pairs. So L is so-called E split Levy subgroup. In the case of GLN, it will be some smaller GLN direct product with tori of order q to the E minus 1. And we have something called E cuspidal, which is like a core. And then you have to take the R, L, G, psi and take the constituents of that delinguistic induced character, and they will be the unipotent characters in a unipotent block. Then comes a very general theorem for all reductive groups, finite reductive groups. If you have a unipotent block, that's the theorem which I just mentioned. Unipotent characters is precisely the constituents of. So this is why we again say that Brouwer equal to Lustig. Maybe I have here. So Brouwer talked about local subgroups, namely normalizers of P subgroups, where you take the modular representation is of over characteristic P. Here, the analog is the normalizer of this Levy subgroup L. It fits into the theory exactly like that, like what Brouwer envisioned. So here's what I said, the example. L will be product of tori and one smaller GL possibly. And then you take the trivial character on all the tori and you take chi lambda, where lambda is an E core in the old sense, and that is exactly the E cuspidal. So as I said, E cuspidal pair is an abstraction of the idea of combinatorial idea of core. Now, if you go away from unipotent blocks to an arbitrary block, then the classification also says that the block determines a conjugacy class S in the possibly dual group, and that's S is L prime now. Then you hope that you will have some kind of Jordan decomposition, that is to relate the block B with the block of the centralizer of S in G star, sharing some properties of B, and that happens in some cases. Now, here are some problems. I say modern problems because Brouwer had a list which could be called classical problems, and they are very old, and some of them are still not solved, especially because Brouwer's problems are for all finite groups, not just these. And sometimes Brouwer's problems are solved for finite reductive groups case by case. which is not what he wanted, but that's the only way we can do it now. But these modern problems are what a lot of people are working on now, and most of them were proposed by Michel Brouet. Now I'm going to say not the technical definition, but there is now, I said sometimes we talk about blocks over K, the field, sometimes over O, the ring. So here are the differences come up. First is when you're dealing with K, the field, then perfect isometry is just some relationship between the characters in the block. So we have to do, that is at character level, the first one. Second one is at module level, where you have to take the algebras OB. I mean, you want to compare the blocks of two groups, G and H, and you want to hopefully one of them may be simpler than the other, such as the normalizer of L. And you want to be able to say there's some connection between these two blocks, and these are the connections we'd like to have. Derived equivalence between the two block algebras when you have something called the abelian defect group of the block. Third one, of course, is the strongest one, Morita equivalence, which often doesn't happen. And here's a very deep theorem, Bonafé-Rouquier, that if we said that the block corresponds to a semi-simple element, if it happens that that centralizer is inside a levy, then there is a Morita equivalence between these two. So we can really concentrate on the case where that doesn't happen. So here is some information about the perfect isometry, which is at the level of the field K. You have two groups you want to compare, then you get these consequences if you have so first of all you must have an isometry, that is the characters in one block, the irreducible character will go to an irreducible character up to sign. Right? Then you will have an isometry with respect to the usual inner product. And then they will have the same number of ordinary characters, they'll have this property of the Cartan matrix and so forth. So this is why as a first step, of course we would really like to have the derived equivalence, but as a first step we'd like to have this. So some results. There's a paper which we call BMM, Brouet, Mahler, Michel, that when you have abelian different groups, if you G is the finite reductive group and H is the normalizer of a levy, the same levy that we talked about before, which is associated with the block, the E cuspidal pair. And then you have, for unipotent blocks, perfect isometry. And this is an old paper of Raphael Rouquier. If you have two symmetric groups and blocks are so-called equal weight, you have, and Michel Angouar. And then there are some stronger results due to Joe Chung and Raphael Rouquier, that you have the abelian defect group conjecture for general linear groups. Now, my talk really starts here. So, going back to the last slide, see that you have perfect, so two symmetric groups, two general linear groups. So usually one tries for G and H, being G is this fixed finite reductive group. H could be a subgroup like that, normalizer of L, or two symmetric groups, which, in other words, in both these cases, you have the type A situation. So now the question is it possible to have perfect isometries between groups which are of different lead types? So at first sight, if we look at a simple example, GL4 and SP4, and I take the case L, remember L has to divide, E is the order of Q mod L, that is L divides Q to the E minus 1. In this case, L divides Q squared minus 1, so it will divide either Q plus 1 or Q minus 1, and I'm taking L divides Q plus 1. And there is actually some correspondence between the principal blocks. However, GL4 has only 5 unipotent characters, SP4 has 6, and you might take these two blocks and make correspondence, the ones with the 5, but 1 is left over. So we don't know whether that question can be answered. Oh. Yes. Now, I got this inspiration from p-adic groups. This is a quotation from James Arthur, the guru of the trace formula, who says, we shall describe a classification of automorphic representation of classical groups in terms of those of general linear groups. So they talk about the principle of endoscopy. Hope I'm pronouncing it correctly, but which means comparing G and then some centralizer of S, something like that. And we too in finite groups have the same concept, comparing G and centralizer of S, except we never use the word endoscopy, which I want to use now. I think I myself am a little frightened of that word because it really means that the doctor is looking inside you with the tube. And the second inspiration is Walsperger's papers. There, in fact, Walsperger pointed me to this paper of Jim Arthur where this quotation appears. He said he was inspired by Arthur. And Walsperger usually writes about p-adic groups, but he does have a couple of papers on finite groups. So I'm not only inspired, but I use his result. So in order to get this correspondence between different types, I have to enlarge the set of unipotent characters. So remember we said that the set of irreducible characters is the union of Lustig series. So Walsperger defines a character to be quadratic unipotent if that S has order 2. Squared is, and in the case of classical groups, if you take the natural representation, it would mean that S has eigenvalues 1 and minus 1 only. And of course it includes the unipotent because S can be 1. So now GLN and UN, let's take them together, and I call it GN, and as I said, always Q odd. Just as unipotents were parameterized by partitions, quadratic unipotents are parameterized by pairs of partitions. So essentially they are constructed by unipotents. You take induced from the Borel of the trivial, for GLN at least, not UN. UN you have to do a little bit more. Here you take for the torus character of degree 2 and then lift it to B and induce. So essentially that's what we're doing there. And now if you take the symplectic group, first of all the unipotent characters are parameterized by these symbols which we had, 2 rows of subsets of integers, and the quadratic again are parameterized by pairs of symbols. It's a little more complicated construction here. One difficulty in the case of symplectic group is, in the case of GLN, the product of 2 GLs, smaller GLs, a subgroup which is a product of 2 GLs is a Levy subgroup. In the case of the symplectic group, product of 2 symplectics is not a Levy subgroup. So we have a problem there. However, we can still, that's Waltz for J constructs the quadratic unipotent characters parameterized by symbols, pairs of symbols. And now the S I said over in the dual group. If you take the symplectic group, the dual group is SO 2n plus 1, and there if you take an element of order 2, each centralizer can be disconnected, and then that's also a problem here. So now the pairs of partitions, from there we go to another parameterization which is by 4 tuples. The quadratic unipotents are parameterized by M1, M2, row 1, row 2, and here the idea of behind this is the idea of cuspidal and Hecke algebra, because M1, M2 essentially refer to some cuspidal representation, and row 1, row 2, as I said, they are representations of Weyl groups of type B. So you have a pair of Weyl groups of type B, and you have this equation M1 times M1 plus 1 over 2, etc., equal to n, which simply talks about, it just comes from small, as I said, smaller GL and some tori. And also another combinatorial interpretation is M1 row 1 is 2 core and 2 quotient of mu1. So for example, I've given what is the parameter. If you take 4, 1, 1, then the parameterization is 2, 1, and then 2 representation. And the 2, so I just want to point out that the 2 refers to the fact that the cuspidal partition is triangular, like A minus 1, A minus 2, etc., going up to 1. And this is 2 is the largest part of the cuspidal representation. So that's the interpretation for M1 and M2, the largest part of the cuspidal. And row 1 and row 2 are like representations of Hecke algebra. But not quite, because sometimes we'll have Deligne-Lustig induction. And similarly, he parameterizes the ones for the symplectic group, H1, H2, row 1, row 2, and with some equation like this. And then, and this is rather easy, but it's what I use critically, there's a bijection between these pairs. So let me go back here. You have some equation forget about n1 and n2, h1 times h1 plus 1 plus h2 squared is n, and some equation here. So it's like two ways of having a quadratic form. And so he sets up a bijection between these cuspidals. So the second one is the bijection, but that's not that's rather technical. So what I have done after that is extend it to, so Gn is GLn or Un, Hn is the symplectic group. So you can now, using the parameterization, extend Walsh-Vezet's bijection for the cuspidal to bijection of irreducible, of quadratic unipotent irreducible characters, however not the same n. N for GLN and some other m for SP. So here's an example. Although SP4 has only 6 unipotent characters, it has 23 quadratic unipotent characters. And of this, 14 of them are in bijection with GL4, 8 with GL3, and 1 with GL2. And there is this unipotent character which was left out when I looked at that initially, and that, because I said GL4 and SP4, GL4 has only 5 unipotents, SP4 has 6, but that one which is left out goes with the quadratic unipotent, and which is quite surprising. So you notice that with 4 you have GL4 and GL2 at the bottom, and something in between. That's the usual pattern. And this with GL2n, you will go with SP2n, you'll start with GL2n and go with GLn. And this sort of reflects the fact that on the one hand GLn contains SP, and on the other hand SP contains GLn. And now if you go the other way, GL4 has 20, and of course 14 we saw goes with SP, 4 with SP6, and 2 with SP8. So from SP you go down, and from GL you go up. And this is some technical. Now this can be just put in one equation as if you take the category of quadratic unipotent representations, then with the usual inner product. So because with each n, with n you don't have n, you have some m, so you take them all together, so you have an isometry between the sum of Grothendieck groups of GL on one hand and symplectic on the other hand. Now, Hecke algebras have to come in, right? Otherwise this audience will be disappointed. So both are isomorphic to, first, because I have the M1, M2, a free abelian group on n cross n, and then you have the two Hecke algebras of type B. However, I have to point out this is a little sloppy because with GL and the parameters are different for GL and SP. Now, in a recent paper which appeared last year, I also generalized first we had the theorem on unipotent blocks only for connected center, and then I generalized it in a paper which appeared last year to quadratic unipotent blocks. In the case of these classical groups, they are called isolated blocks. So here you will have to take for the quadratic unipotent, then you take some tori and then a smaller sp, and you will have to take the trivial character for some of the tori, the sign character for some of the tori, and then course as before. Now, so quadratic unipotent clocks are classified by E course of phase and weight. So it's also common in the case of the symmetric group and so on to talk about core and weight of a block. And so the core is the lambda 1, lambda 2, and well, or the you could say the whole psi, and then the weight is the pair m1, m2. Now this looks like an innocent theorem, but behind that, I mean, I used some of Wolfsburg's results, and behind that is the theory of Lustig's character sheaves. So it's quite a lot of deep stuff has to be used there. Mainly because you had that disconnected group, and therefore extensions to the disconnected groups are not unique, but with character sheaves you can make a compatible description combinatorially. Now, this is the, now I'm coming to the main theorem. We compare, I'm starting with the, so I have to take Q greater than N for the SP because of the character sheaves situation. Hopefully that may be removed sometime. If I take, I'm comparing the unitary group and the symplectic group. Taking the or GLN and the symplectic group. And your E has to be even. Either E is 2F or F is odd, which F odd I put above, or E is congruent to 1 mod 4 and L divides Q to the F plus 1. There's one case excluded, not because there are some problems, but it's not true in that case. It's theorem. So let's say stick with the case E is 2F, F odd. Then this is the theorem that if you have a quadratic unipotent, so this bijection between characters which I described, now the main point here, even if you don't look at all the technicalities, the main point is it carries over to these blocks. So there is a correspondence between blocks B, capital B of GLN or UN and small b of SP, and there's a natural bijection between the quadratic unipotent characters. So the correspondence is between a certain labeling of the blocks. And when you have abelian, the defect groups are isomorphic because I choose L divides, say, Q to the F minus 1 in both cases. And I have the abelian defect group. And then using the work of BMM for unipotent blocks, you also get the perfect isometry. So we're still over K. And this can be written as follows, that there is a bijection between the union of blocks n greater than or equal to 0 for Gn, which is GLN or UN, and union of blocks for symplectic group, and natural bijection between the quadratic unipotent characters in those blocks. So the idea is I'll go through this quickly. You go to the core and the weight, and then the core, you take the the core is a certain character which corresponds to a certain core in the case of symplectic group, and then you go to the, so block to the core, should say core and the weight, core and the weight, and then to the other block. So this is what I said, that use the paper of BMM to get a local subgroup, and the local subgroup is the same, and therefore you go to the other block. Now I come to another way of describing this by endoscopy. Anguar very recently, it's not published yet, it's on his web page, shows that if you have G and if you have S, semi-simple element in G star, he has a group G of S such that you can make a correspondence between blocks. So G of S essentially is like centralizer of S. It's a dual of the centralizer of S. Example that if you have SP, G of S is the product of a symplectic group and an orthogonal group. That's in the algebraic case. When you go to the finite, it can be plus or minus, which we can figure out. So now the idea of introducing the endoscopy group is that you get a correspondence between a block of G which corresponds to S and a unipotent block of this G of S. So you reduce to unipotent blocks. So therefore now, if you don't like quadratic unipotent block, you can just go to this situation, and then you can say there's a bijection between pairs of GLs, unipotent blocks of pairs of GLs, and pairs of pairs like this, SP cross O. But notice that, suppose you just take on the right hand side just SP, which is also possible, you may not get correspondingly one GL, you may get a pair, as we saw before. And there's a natural bijection. So this is, now you're reduced to the case of unipotent blocks by using Anguar's construction. So this is the final summary. Which the first says that there is this character correspondence, second says there is a block correspondence between these. Now we had this, when you look at this SP cross O, we had this 4 tuple H1, H2, N1, N2, Walsh-Jace parameterization, and then you can now see that if you have the pair H1 and N1 go with the SP, H2 and N2 the pair go with the O, and then you can say if H2 is even, you get the O plus, and if H2 is odd, you take the O minus. So you can figure out which one you take. Now, unfortunately, H1N1 now refers to swine flu, so so it's not my, therefore, but it's not my notation. So we're almost at the end. And the same thing for suitable L. The blocks, quadratic unipotent blocks, if you want to take the whole group G, you have to correspond quadratic unipotent blocks. And if you want to take unipotent blocks, you have to take pairs of groups. So, work in progress, for which I hope to talk to people here, is so far I only had the perfect isometry. What more can you say? Can you have derived equivalence? So this would be, as I said, across types. Derived equivalence. Morita equivalence already I know we don't have in general. But there should be, should be more to say about these corresponding blocks. And finally, I want to quote Hermann Weyl. He said, "General linear group is the all-embracing majesty." But now it looks like symplectic group has equal status with the general linear group. But I don't know what to call that group. Okay, that's the end.
Thank you very much, Bhama. Any questions or comments?
When you have this product SP times O in a good situation, SPN or OM, you have the how correspondence, and you have also how correspondence for GL. GL, it's also a dual pair. So is your correspondence compatible with that, or in some sense?
The dual pair?
It's if you use a Weyl representation,
Weyl.
very strict, you have this how correspondence, which will give you a representation of SP times O on one hand, but you can also get GL times GL as a dual pair.
That's interesting. Yeah, I haven't looked at that, but maybe there is something there, because there was a slide where Walsh-Boucher defines the bijection between M1, M2, and H1, H2. That's exactly, he takes that, essentially that definition, from your paper with Anne-Marie and Jean-Michel, which is to do with the how correspondence. So maybe there is something there. Yeah. Should I look at that?
Comments? If not, we meet again at 11:30 after coffee. Thank you very much.